Now we are live. Okay. So, just a minute here. Okay. Everyone is seeing the screen on the Meet, Google Meet. Okay. So this is gonna be the first presentation given by Sabrina. Sabrina is a new member of our team here. She's a master student, and she will talk a little about the Dodelson's book. She's studying the little of cosmology in order to study dark matter and quantum field theory and particle physics, especially. So she'll give a brief overview of the first chapter of Dodelson's book, and it's her first presentation in English. So,
So first, hi, my name is Sabrina Brigida, and today I'm going to talk a little about what I've learned by reading the Dodelson's book on modern cosmology. And I will read this book for, I think, 6 months, basically, and I will do in a presentation once a month. So, and I need to say that my English is not that good. I'm not fluent yet. I don't speak almost nothing 2 weeks ago. So, but I will try to, do my presentation in English today. So today I'm going to talk about the Concordance Model of Cosmology and the Expanding Universe. That is the first chapter, basically, of the Dodelson's book. And okay, I'm going to start. These are some topics about this book. So here we have the BBN, that is the Big Bang nucleosynthesis. So we have the Hubble diagram that basically will help us to understand the expansion of the universe. This chapter talks about CMB, the cosmic microwave background, a little about the structure of the universe, so introduce perturbation and all this stuff, and talks about lambda CDM, that is a concordance model of cosmology that we know today. That CDM, it means cold dark matter in this case. And I will talk about metric, that is more about the chapter 2, and the chapter 2 talks about constituents of the universe and the evolution of the universe. So I'm going to talk a little about these topics today, not all day, but a little about some of these topics. So first, about the expansion of the universe. So to try to explain the expansion of the universe, we need to introduce a parameter that is called the scale factor. So the scale factor, how I put here, it quantifies the expansion of the universe. So it's determined by a letter, that is the letter A. And at the present time, we consider for a convention that the scale factor is equal to 1 at the present time. So at earlier time, for the convention too, we consider that the scale factor is smaller than 1, for example. So for earlier time, the scale factor is smaller than it is today. And to try to quantify the scale factor, the evolution over time of the scale factor, we use the Hubble rate that is defined by this mathematical expression here. And when we talk about the expansion of the universe, we are talking about how the distance between galaxies is increasing over the time. So the physical distance in this case is proportional to the scale factor, okay? So we have an expression, a mathematical expression, that say this to us, that the physical distance between galaxies is proportional to the scale factor. The scale factor is evolving with the time. And we have an phenomena that happens in expanding universe, that is the redshift of light. So, for example, for an observer, they will see the wavelength of the light longer than the wavelength of light that was emitted by the galaxy. So this is the redshift effect. And mathematically, we can explain this effect with this equation here, where z is the redshift, and lambda is this lambda up is the wavelength that we observed of this galaxy, and this other lambda is the lambda that the galaxy emits. So this is a mathematical form to trying to quantify the redshift, this effect. So, okay, there are other parameters that characterize the... Oi?
Você tem que voltar Vou aceitar o pessoal que está pedindo para entrar.
Tá.
Tá no Meet?
No Meet.
Esse Google lá embaixo.
Cadê?
Lá em cima. Na outra aba.
Ah. Tá. Okay, so to characterize the universe, we have another parameter that we call the geometry in this case. So there are three possibilities of geometry for the universe. We have an open universe. We can have an open universe in this case that has negative curvature. We have a closed universe that had positive curvature, and an Euclidean universe that we can also say that is flat, that has no curvature. So we have these three types of possible universe, of possible geometry for the universe. And the Dodelson's book gives us an interesting example. So they consider first two particles traveling parallel one each other, side by side. And he says that for an Euclidean universe, this trajectory are always parallel one to each other. So, but in an open universe, for example, the trajectories over time will diverge. And for an enclosed universe, the trajectory over the time will converge to the same point. So this is a way more intuitive to try to understand the possibilities of geometry of the universe. So when we are talking about space, we need to talk about metric, okay? Because with the metric, we can measure the distance between 2 points in space. Is a way that we can use this to try to measure the distance between 2 points in space. And here, for example, we have a metric for an expanding universe, okay? So here, that metric will dependent. It's dependent of the scale factor squared. That is dependent to over the time. So we have this metric here. And another example of metric is, for example, a metric in a 2D plane. So here, for example, we have a metric to Cartesian coordinates. And here above, here down, we have a metric for polar coordinate. So they are different because the metric will depend on the coordinate system. So that's why we have for the same plane, that is 2D plane, metrics different because they will depend on the coordinate system. But in characteristics, in other characteristics, is that the distance is invariant for a space. That means that the distance that we can measure with the metric is independent on the coordinate system. So we have this characteristic about the metrics. And for example, I put here too, that for a curved space, we had this shortest path between 2 points as being measured by a geodesic. So in 2D plane, this is a straight line, but in a curved space, this is geodesic. So it's not a straight line curved space. This is the Hubble diagram, for example. So with the Hubble diagram, we can try to understand the expansion of the universe. We relate with the Hubble elementary law the velocity of the galaxy with the distance of this galaxy. So this is proportional to this constant, that is Hubble constant, that we can define in the present time. So this Hubble constant, H0, is defined as the Hubble constant at the present time. So T0 is the present time. This is the definition. So here in the side, we have the Hubble diagram. So we have for each point here a galaxy, and in this issue, in this side we have the velocities, and in this side we have the distance. So you can see that we have a linear relation between the velocity and the distance. So here we have three straight lines. That is like a prediction that we can do with the Hubble elementary law. So this is about Big Bang nucleosynthesis, that I think that is more difficult to understand. Is complex. Basically, BBN, that we call, is a process, like I put here, of formation of light element in the early universe. Okay, so first, in the early universe, we have a universe that is very hot and dense. So we have a high energy radiation that destroyed the nucleus that formed it. So we cannot have neutral atoms at this time. Okay. The temperature is approximately 1 MeV per kb, where kb is the Boltzmann constant. So basically today we know that baryonic matter, it doesn't represent all the matter that we have in the universe. Okay, so it represents approximately 5% of the critical density of the universe. And we have a big question today, that is, what is dark matter? We don't know. We need a dark matter because the matter of the universe is not only baryonic matter that we can see, that we can detect too. We don't know yet, because the dark matter, it represents, I think, 25% of the matter of the universe. So we need to answer what is the dark matter in this case. We don't know yet. So the BBN can give to us this hypothesis of dark matter in this case. So that's why we need a model in cosmology that we call lambda CDM, that it means cold dark matter, that we consider some ingredients to this model, that is cosmological constant, the part of inflation that can try to explain to us how the universe was expanding exponentially in the initial, and the CDM, that is the cold dark matter, that can help us to try to understand how these structures were formed. And in this model, we consider too an Euclidean universe that is flat in this case. So that's why we need this model today. We don't know yet what is dark matter, and we have a cosmological constant that is related to dark energy, that I think that represents 17%, I think, of the components of the universe. So we need this model to try to explain all these things, and we have this today. So I think that is it.
Yeah. Could you explain what is the critical density?
The critical density is
Before.
sim, sim. It's here now. So the critical density is like when you take all the density of the universe, of the all components, so you have a critical density. For example, for a flat universe, the critical density is approximately 1. And we can take this critical density and take in relation with the energy of the universe, and this will acho que eu não sei falar isso em inglês. E com isso a gente pode relacionar a densidade crítica com a geometria do universo, nesse caso. Então, a gente utiliza essa densidade crítica para tentar entender a densidade de energia do universo.
Usando o parâmetro de densidade.
Isso.
Basicamente, só para complementar, você entender um pouco melhor, I will talk in English. Yeah. If I say in English, you understand, right?
Mm-hmm.
Okay. Because basically, this critical density is a parameter, and that's when you are. It's because the Dodelson books still not present the Friedman equations, and so that it's not. He talks about in his first chapters about the critical density, but it did not show what the critical density actually
define the critical density
Yeah.
as the density of a universe, a flat universe.
Yeah, exactly.
Yes.
The critical density is basically the density you need to have in order to have a flat universe. If your density is different of that critical density, you will not have a flat universe. You will have or a closed universe or a open universe.
Yes.
So, for example, when you have the density parameter, you put the density of material that it's important for you, and divided by the critical density. So is there in that sense, if the universe is flat, this represents the percentage of that material that you're considering. Because the universe is flat, so the critical density, it has a number, I don't remember what it is, but this critical density is just the density of all the material inside the universe for it to be flat, for its geometry to be flat. So it is approximately flat, so you can consider this to be the density of the universe. Okay. Just another question: can dark matter, the whole dark matter, be bionic?
I don't think that can be, because baryonic matter is constituted of protons, neutrons, and we can detect this directly, and we are in contact with this too. We can observe it visually, and the dark matter we can have a gravitational effect, so we can observe directly, I think.
I think the thing is that baryonic, it brings me the idea of quarks, and quarks would interact extremely strongly with them.
But in the context of cosmology, baryons are
Electrons,
everything.
quarks.
It's not the model, right? So
No,
the
no,
only
but-
thing that could be would be a neutrino. That's very small.
No, but since she's talking
Neutrino
about
is right.
cosmology, when we say baryons, cosmology, it's not in the context of
Cold.
strong interaction. Baryons are everything
Yeah,
that
everything that
Everything except radiation.
we don't,
except radiation. Yes, electrons, protons,
because
everything.
the whole standard model, we don't have a dark matter candidate in the standard model.
Yeah,
Except
Yeah.
neutrinos, that could be a small part of it.
I'm asking this because of BBN. Because the BBN said the total amount of baryon matter that you get. And this is not even close the amount of dark matter that you need. So I'm just asking because of that.
Because I mean, it's a really important feature of prediction of BBN that you have a lot. I mean, you have a lot more matter than the baryonic matter.
Mhm.
So when you compare the results of BBN with the results coming from CMB, so you can assert the quantity of dark matter and dark energy that you have you need to consider in your lambda CDM model. But,
Which is the quantity that you said, 25% of
Yeah.
of the density material.
Congrats. English.
Thank you.
Amazing English. Okay.
Thank
you.
I have
Yes, very
a
good.
just a simple
Yeah.
question. Is this a matter of understanding future? Right. So can you tell me why do we need inflation? Why is it something that we need in the model?
I think that the universe begins to expanding a lot fast. Okay, so the inflation comes to try to explain the exponential growth, the exponential expansion of the universe. So maybe we need this to try to understand to maybe perturbations. I don't know with confidence in my answer. I don't have confidence in what I'm saying, but I think that that's because this.
Yes. Well, it's correct. In inflation, the universe expands exponentially, but inflation is not necessary to explain the exponential growth of the universe. Because the inflation period is defined as a period of exponential inflation. You're correct when you say that it explains very well the perturbations that create uh, structures in the universe. But I think the main motivation, the one that I like the most, there are many. I was wondering if you could tell me one. Is about causality. Because well, what exactly do I mean by that? So you know CMB, right?
Mhm.
What is the main feature of CMB? Can you tell me?
Future significant
Feature.
feature.
Característica. A principal característica dessa medida.
The radiação do corpo negro.
Yes, and it has a very well-defined temperature,
Yes.
which does not have, it oscillates very briefly in the whole patch of space. But if you consider the CNB as the whole space, it is very unlikely, you can say, that everything has the same temperature because different patches in the sky are not causally connected, which means that they were never in causal contact. They never communicated with each other. You see?
Mhm.
So inflation comes as a mean to overcome this. So basically what inflation does is say that, okay, so everything starts causally connected. So everything will start causally connected. And then you expand the universe uh, in an accelerated expansion, which is the exponential one. And patches of the sky become causally disconnected. Because when we look at the sky today, if we have a starting point for the universe, which we usually say it's at the end of inflation, when we consider the lambda CDM model, which is like the beginning of the radiation era. I think you've seen this, maybe that the universe has different eras of illumination, radiation, matter, everything. You see that those patches were never connected. But if you state that there was an inflationary period where everything was connected, you solve that problem. And magically, it solves other problems such as the structure formation and everything appearing there. But I think, for me, my opinion, there are other problems such as the flatness problem, yes, which is a problem de... Eu me esqueci o termo para isso. But the one that I like the most is the causal connection because you see it very easily at the beginning. Fine tuning, thank you. At the beginning of your cosmology course, of cosmology, when you define distances, which we will define in the next chapter of Dodelson, you see that patches of the sky are not causally connected. And inflation solves it
I think you see that in maybe chapter 7.
Yeah, inflation is very,
Dodelson. It's
very late.
Yeah.
But,
But I think that the book discusses all the details of why we need inflation. I mean, we can have another non-standard cosmologies like the Dodelson cosmology, but I mean I think that the inflation is
inflation is the most accepted.
Yeah. I mean there are others, but I mean people already study a lot of inflation and it gives what we observe.
Yeah, what I like about inflation, you don't prove it, you don't see it directly.
Yeah.
It's just one of those things that, well, it's the theory that explains basically everything. You don't prove it directly, but it's the one that best fits the model. So that's the main thing I wanted to make sure and make you familiar with it. Maybe.
Okay, thank you.
So thank you, Sabrina.
Thank you.
I will end up the stream here. So thank you. But the people on the meetings continue here because I will start another one. So thank you.